Hello. Am I audible? Let's wait for 2 more minutes. If few people. I think I should start now. It's already 5:05. So today I will solve time independent Schrodinger equation, and we will also solve few problems regarding infinite potential well and harmonic 1D harmonic oscillator. So I'll start with the basic theory of infinite potential well. Let me share my screen. Yeah. So I hope my screen is visible.
Yes, sir.
So the time independent Schrodinger equation for 1D is given by this equation plus V psi equal to E psi. So to solve this Schrodinger equation, we need to the form of this potential. So we'll show few example. The first one is the infinite potential well. So the diagram for the potential is 0 to a. At 0 and also at a, there are two infinite barriers. This is x direction. This is the form of Vx, and the form of Vx is of this kind, that Vx is 0 from 0 to a, and it is infinity otherwise. So the Schrödinger equation for this 1D potential will reduce to this form. Psi is outside this potential well, psi is always 0. Here is also psi is 0, and here psi is 0. We need to find the form of psi inside this potential well. Now inside the potential well, the potential is 0, so this term will not contribute, so we are left with this term. So we will solve this equation, d2 psi dx2 plus twice m e by h bar square psi equal to 0. So we can write this as dx2 plus k square psi equal to 0, where k square is 2m e by h bar square. Now the solution of this differential equation is very easy to show, that it is a sin kx plus b cos kx, where a and b are arbitrary constants. So this is the general form of this wave function, but the boundary condition is that psi at 0 equal to psi at a equal to 0. This is the boundary condition for this potential well. So from the first condition, that psi at x equal to 0 is 0, we get this implies that b has to be 0, because at x equal to 0 this term is already 0, so b is 0. So our potential, so our wave function is a sin kx, and the second boundary condition implies that psi a is 0, which implies that a sin ka equal to 0. Now a can't be 0, because if a is 0, this wave function is always 0. This is a trivial, so this can't be true. So ka should be equal to n pi, which implies that k equal to n pi by a. So from this we can get the energy, that energy is here, from here we get that E equal to h bar square k square by twice m. So if we put the value of k here, we will get the 1 minute. Sorry, there was a call. So the eigen energies are En equal to n square pi square h bar square by 2m a square. From this expression we get the eigen energies, and since k equal to n pi by a, so the wave function is psi equal to a sin n pi x by a. This is the wave function, and if we normalize this, the normalization condition is 0 to a mod psi square dx equal to 1. Applying this condition, we can easily find that the value of a is root over of 2 pi by a. So the wave function psi x is root over 2 by a sin n pi x by a. This is our wave function for infinite potential well, and this is the eigen energies. to solve problems we need to know these two expressions. And similarly, for harmonic oscillator, we can solve for eigen energies and eigen function. So for harmonic oscillator, diagram. Sorry. This is something like this: Vx at 0, this is x. The potential energy for 1D harmonic oscillator is given by half m omega square x square. So the Schrodinger equation will reduce to, we can write this term in terms of momentum operator, because P is h bar by I del x. So if we write this Schrodinger equation, we can write it this way, putting the value of potential energy. We can write it in this way, and we can solve this problem into different ways. One is the algebraic method. So to solve the algebraic method, we will write two operator. We will introduce two operator, a plus and a minus. Pooja Gupta was asking for recording of the previous class. Actually, I forgot to record the previous class, so I started recording from this class only. So there is no recording of the previous class actually, but I can share the video links, the videos of 4 questions that I have solved in the previous session. Okay, so we will introduce to operator a plus minus, which are given by minus plus ip plus m omega x, and the commutator relation between these two operator is this one. So introducing these two operator, the Hamiltonian, this is our Hamiltonian. The Hamiltonian will reduce to h bar omega a plus a minus plus half. So this is a really lengthy process to solve all the way. I will not going to solve this problem. You can find it in any classic in any quantum mechanics book, which I need the final solution. The final solution is the wave function are given by this equation, 2 to the power n factorial n hn xi, where hn is Hermite polynomial and xi is root over of m omega by h bar x, and the eigen energies for harmonic oscillator, if we solve the Schrodinger equation all the way, algebraic method, this is the algebraic method, this is easier, and there is another method, analytical method. In that way we can also solve the Schrodinger equation, and after solving this we get that the eigen energies are given by this form, where n are integer values starting from 0, there is 0, 1, 2 and so on. As we have discussed in the previous class, that for half harmonic oscillator the eigen energy is same, but the allowed values of n will start from 1 and only odd values are allowed, because the condition for half harmonic oscillator that psi n 0 psi n at x equal to 0 should be 0, and this will implies that the Hermite polynomial at x equal to 0 is 0, and this condition is only satisfied for n equal to 1, 3, 5, that is odd value of n.
Sir,
So
from where we find the value of n is equal to 1, 3 for half harmonic oscillator?
yes, because the form of if we see the form of harmonic oscillator, then
Mm.
for hn, I have discussed it in the previous class also, that hn xi hn 0 this is 1, h1 if we write in function of x, and h1 x is x, h2 x is 4x square minus 2, and so on. So if we put x equal to 0, then h00 is 1, it is not 1, sorry, it is not 0, h00 is not going to be 0, so this condition is not satisfied for n equal to 0. Similarly, for n equal to 2, this is n equal to 2, right? So for this also h20 is minus 2. Am I getting 0? No. So for n even values, for h0 are not 0, so this condition is not satisfied. So if this condition is not satisfied, then it is not allowed, right? Then the values of n are not allowed, so n equal to 0, 2, these values cannot be allowed. But for for n equal to 1, which is an odd value, this h10 is 0, because if we put x equal to 0, this is 0, so this condition is satisfied, right? So this condition is only satisfied for n equal to 1, 3, 5. So from this argument we can say that only the odd values of n are allowed, because there is a boundary condition that this has to be satisfied. Is it clear?
Yes, sir.
Yeah, so from the eigen energies and eigen functions, we'll try to solve few problems. So I'll run the first problem. Let me one minute, I have to stop sharing here. Yeah, can you see my screen?
Yes, sir.
Okay. Let me know if the sound is clear or not. In this video, I am going to solve GATE Physics 2011 question number 13. An electron with energy
Not clear.
E is incident from. It's not clear?
Yes, sir.
Okay. Okay, let me run it again. It's still not. In this video, I am going to solve GATE Physics 2011 question number 13. An electron with energy E is incident from left on a potential barrier given by Vx equal to 0 for x less than 0 and Vx equal to V0 for x greater than 0, and the potential barrier is shown in the figure. Is it still not clear?
Yes, sir.
Have you tried to turn on your volume to 100%?
Yes, sir. It's already.
But
I only.
still not like audible.
Yes, sir. So can you solve this question in book screen?
Yeah, okay. Okay. But the sound is good to me. What is the problem? For E less than V0, the space. Try to listen for 1 minute and let me. Part of the wave function for x greater than 0
Okay.
is of the form where alpha is a real positive quantity. So in this question, what we need to do is to find the wave function for x equal to x greater than 0 part. So for to find the wave function, we need to solve the Schrodinger equation. The one-dimensional Schrodinger equation is given by this one plus Vx psi, where V the potential is dependent on x coordinate, equal to E psi. We are asked to find the wave function for x greater than 0. So for x greater than 0, the potential Vx equal to V0. We'll put this in the Schrodinger equation. What we find is d2 psi dx2 plus v0 psi equal to E psi. Here we have given that E is less than V0. We have to keep this in mind. So now let's solve this. Minus, we will multiply by minus 2m by h bar square in both sides. So minus 2m by h bar square v0 psi. Sorry, I have got text message. Try to reconnect, the problem may get solved. Sorry, I did not get your. Try. Pooja, can you unmute and say? Oh,
Yes, sir.
yeah. So you are saying to try to reconnect. I mean,
Try to reconnect yourself and then get back in the meeting, sir.
that will solve the question. That will solve the problem.
Your voice is not coming properly.
Okay.
Sir, I have a question.
Yeah. Ask.
I have asked this that this GATE 2023 preparation, is this course helpful for that?
Yeah, definitely. I mean, I am going to solve quantum mechanics questions from the past few years, like starting from 2010. So the pattern are almost same for every year. So that will be definitely helpful for 2023 GATE exam. Similar
Yeah,
kind
okay,
of
sir.
questions they are asked in GATE question. Okay, I'll solve it live if the sound is not clear.
Now your sound is clear, sir. I think when you start presenting your screen, the problem may arise from there.
Okay. Okay, let me share a different question and see if the problem is still persist. Wait. In this video, I will solve GATE Physics 2012 question 5. A particle of mass m is confined in a two-dimensional squirrel potential of dimension a. This potential Vxy is given by Vxy equal to 0 for x between minus a to a and y between also minus a to a, and infinity elsewhere. The energy of the first excited state for this particle is given by the correct
Sir, voice is
option
not clear.
to be chosen. Why is it not clear? The
Yes,
question is that then I'll solve the question. The potential is 0 for minus a to a and y from minus a to a. Okay, I'll solve these questions live.
Okay.
Screen. What I have solved it, so I can just tell you. So the problem is that an electron with energy E is incident from left on a potential barrier given by this potential barrier, which depicted in the figure. So what is asked in the question, to find out the space part of the wave function for x greater than 0. So we'll need to solve the Schrodinger equation for to find out the wave function definitely, and we are only asked to find the wave function for x greater than 0. So we'll do that for x greater than 0. So for x greater than 0, we can see that Vx equal to V0. So we'll put this value of Vx in the Schrodinger equation. That is what I have done in the solution, that Vx equal to V0. So d2 psi dx2 minus 2m by h bar square V0 psi equal to minus 2me by h bar square psi, and I'll take this part in the left hand side, and since E is less than V0, this was mentioned in the question that E is less than V0, so this whole value needs to be positive. We can write it in that way also, that instead of minus sign we can write it that plus 2m by h bar square E minus V0, but in that case this will be negative. So that is why I have written in this way minus and then V0 minus E. In that way this value is positive, because we will write this in terms of a square of any number. So alpha, we have replaced this value as alpha square, and if we take psi in the form of e to the power mx, then this equation we get, and from this equation we can see that m equal to plus minus alpha. So the form of the wave function can be a e to the power alpha x plus b e to the power minus alpha x, or a or b are arbitrary constants. Now the boundary condition for this, that since psi need to be finite at any value, so if x goes to infinite, this term diverges, because it is a e to the power alpha x. So if x goes to infinity, then this term is diverges, but that can't be true. So a must be 0. So if a is 0, then psi is e to the power minus alpha. Psi is proportional to e to the power minus alpha x. That is, it is a decaying function. So option B is correct for this problem. So this type of question is asked in GATE question, and it is very easy to solve. Just you need to solve the Schrodinger equation. So do you have any question?
No, sir.
If not, then let's move to the next question. And since the sound is not coming in the videos, I'll solve the next question live as well. So in the next question is GATE Physics 2012 question 5. This is also regarding this is regarding a two-dimensional square well potential. So this will cover the topic I have discussed earlier. So the question is, a particle of mass m is confined in a two-dimensional square well potential of dimension a. This potential is given by this form, that Vxy equal to 0 for x in between minus a to a, and y is also in between minus a to a, and infinity elsewhere. So the energy of the first excited state for this particle is given by which? So we have solved one-dimensional potential well. Similarly, if we solve two-dimensional potential well, we can see that the energy value, eigenenergy, this is for one-dimensional potential well, right? That En equal to n square pi square h bar square by 2ml square. For 2D, instead of n square, we will have nx square plus ny square. This is the eigenenergies for 2D infinite potential well. And in our case, this is start from minus a to a. So the length of the barrier is 2a. So L is here 2a. So if we solve it, then we get that En equal to nx square plus ny square pi square h bar square divided by 2m, and L is 2a, so 2a square. So nx square plus ny square pi h bar square by 8m square. Now what we asked is to find the first excited state energy. So for 1D potential well, we saw that n is equal to 1, 2, 3 and so on. So here also nx and ny will start from 1, and the only integer values are allowed. So the ground state energy would be nx equal to 1 and ny equal to 1, since this is the lowest value. So this is the ground state energy, and the first excited state energy is nx equal to 1 and ny equal to 2. And if, similarly, if we take nx equal to 2 and ny equal to 1, then also our energy will be same. So the first excited state energy is doubly degenerate, and the value of the energy is, if we put nx equal to 1 and ny equal to 2, then we get that it is 5 pi square h bar square by 8m a square. So this is the correct answer. I think in the option it should be 8 and not 2. So it was some mistake, I think. But the right answer is 5 pi square h bar square by 8m a square. So it was also an easy question. So if you have any question, then you can ask.
No, sir.
Yeah, I think it was also easy. The next question is from harmonic oscillator, 1D harmonic oscillator. So the question is, a particle is constrained to move in a truncated harmonic potential well as shown in the figure. Which one of the following statement is correct? The potential well is given here.
Sir, what is the meaning of truncated harmonic oscillator potential?
Truncated means that it is, this part is not here. It is truncated to x less greater than 0. That is half harmonic oscillator. It is similar, the word are similar. Half harmonic oscillator and truncated harmonic oscillator are same. There is no part for x less than 0. Only x greater than 0 is there. And the options are that the first option is that the parity of the first excited state is even. Option B is that the parity of the ground state is even. Option C that the ground state energy is half h bar omega, and option D is the first excited state energy is 7 by 2 h bar omega. Only one option is correct. So let's solve this question. The potential is half m omega square x square for x greater than 0 and 0 for x less than 0. This is the definition of half harmonic oscillator's potential. And we have shown in the class that the wave function for harmonic oscillator is psi n x equal to this expression, and the eigen energies En equal to n plus half h bar omega. But since it is truncated harmonic potential well, then the allowed values of n is not 1 2 3 4 0 1 2 3 4 5, is only the odd values, that is 1 3 and 5. Because of this condition, as we have earlier discussed this, so only these values are allowed. And the from this function we can see that the parity, that is psi of n minus x equal to minus psi n x, because sorry this is not for total harmonic oscillator. For total harmonic oscillator, this is the parity relation, that psi n of minus x equal to minus 1 to the power n psi n x, because if we put x equal to minus x, then only this value will change. This is positive, so hn of minus xi, and this is minus n to the power minus 1 to the power n hn of xi. If we see the definition, the Rodrigues formula for hn of xi, that is Hermite polynomial, then you can see that if we put x equal to minus x, then minus 1 to the power n will come out. So this is the parity property for harmonic oscillator wave function. And since only the odd values are allowed, if we put n equal to any odd values, then psi n minus x would be minus psi n x, because n is always odd. So this is the parity property for half harmonic oscillator. This is for harmonic oscillator, the full harmonic oscillator. And this condition is applied for half harmonic oscillator or truncated harmonic oscillator. That is, all the wave functions are odd parities. So option A and B cannot be true, because here the first excited state and also the ground state are said to be even, but for half harmonic oscillator all the wave functions are odd. And the eigen option C and D are talking about eigen energy. So eigen energy can also be calculated, since we know that eigen energy are on the is of the form of En equal to n plus half h bar omega, where n can be 1 3 and 5. So the ground state energy is n equal to 1, and for n equal to 1 the energy is, if we put n equal to 1, then we get that the energy is 3 by 2 h bar omega. So this is the ground state energy, 3 by 2 h bar omega, and not half h bar omega. So option C is also not correct. And the first excited energy, for first excited state, n equal to 3. So if we put n equal to 3, then the energy of the first excited state is E3 equal to 3 plus half h bar omega, and this is 7 by 2 h bar omega. So option D is correct. The first excited state energy is 7 by 2 h bar omega. So for this question, this option is correct. So any question?
No, sir.
So everyone understood this question?
Yes, sir.
Okay, good. then I'll solve the next question, which is GATE Physics 2014 question 31. This is this is also about a harmonic oscillator potential, but this is not a 1D harmonic oscillator, this is 2D harmonic oscillator. And for 2D harmonic oscillator, the question, let me first read the question. A particle of mass m is subjected to a potential V equal to half m omega square x square plus y square, and the state with energy 4 h bar omega is g fold degenerate. The value of g, we are asked to find the value of g. There is no option for this question. This is numerical type of question. The answer would be a numerical value.
Sir,
So
degeneracy.
yeah, we need to find the degeneracy of, for this problem.
Okay.
So degeneracy means how many states are there with equal energy, and the energy is given. The energy is 4 h bar omega. So how many states are there with energy 4 h bar omega? We need to find this. For 1D harmonic oscillator, all the energies are non-degenerate, but for 2D harmonic oscillator, they are degenerate, and we can see that how fold.
N,
If it,
n
yeah,
plus 1.
yeah, it is n plus 1. So Vxy equal to half omega square x square plus y square, and eigen energy En is n plus half h bar omega for 1D harmonic oscillator, and n equal to 0, 1, 2. For 2D harmonic oscillator, the energy, eigen energy is nx plus ny plus 1 h bar omega, where nx is 0, 1, 2, and ny is also integer value starting from 0. Now the given energy En is 4 h bar omega. If you also don't know that it is n plus 1 degenerate, then also you can find it, that the energy is 4 h bar omega, and also it is equal, this is equal to nx plus ny plus 1 h bar omega. So from these two we see that nx plus ny has to be 3. Now in how many ways nx plus ny can be 3, where nx and ny are integer values starting from 0? So the first way is nx equal to 0 and ny equal to 3. Similarly, ny can be 3 and nx equal to 0, and nx equal to 1 and ny equal to 2 will also make the this sum to be 3. Similarly, nx equal to 2 and ny equal to 1 will also make this 3, and there is no other way that the sum of nx plus ny can be 3. So only 4 ways are there. So the state, this 4 h bar omega, is 4-fold degenerate. So this is the, in that way you can find this. And also the shortcut method is that if energy is n plus 1 h bar omega, then the degeneracy and n plus 1. So in our case the energy is 4 h bar omega, so the degeneracy is 4. So this is the shortcut method. In that way you can also find the answer. So this value of g is 4. So this was also easy question. So I have picked 4 questions starting from 2010. So this 4 question was there related to this 1D potential harmonic oscillator and infinite potential well. So only 4 questions I have solved for today. If you have any question regarding harmonic oscillator and this infinite potential well, you can ask. And also you can look at the picture of harmonic oscillator wave function, like the parity I was talking about, that
Sir, for
yeah,
हार्मोनिक ऑसिलेटर और हाफ डिजेनरेट.
half harmonic oscillator, yeah.
Yes sir, yes sir. And value of n, what will be the value of n
For harmonic oscillator, the
in
value
half
of
harm?
in yeah, for half harmonic it is odd values of n, 1 3 5 7 dot dot dot, and for harmonic oscillator it will all the values, all the integer values.
Okay.
So these two you can remember. And also the wave function for n equal to 0, this is the wave function for harmonic oscillator. For n equal to 1, the wave function looks like, sorry, the wave function looks like something like this. For n equal to, this is for n equal to 1. For n equal to 2, the wave function looks like this. For n equal to 3, the wave function is like this. So from the wave function you can also see that for n equal to 0, this is even with respect to x equal to 0. This wave function is even. This is odd parity. This is again even. So from the picture you can also see that for half harmonic oscillator, that is for n equal to 1, n equal to 3, all the wave functions are odd with respect to x equal to 0. That is what I have tried to argue from mathematical argument, that for half harmonic oscillator all the wave functions are odd parity, satisfied odd parity. So if you look at the picture of wave function, you can also see that this is actually true, and you can actually remember this structure of the wave function. This is also sometimes asked in GATE questions. So do you have any question?
No sir.
Anyone else? Have you understood all the questions that I have solved today?
Yes sir.
So in the next session I was planning to solve the remaining potential, well, like the delta function potential and the free particle and some different step potential. Any suggestion on that?
Sir, live video solving video is good. If you solve or recorded video, that's not good.
Okay, you are suggesting that solving the questions live, right?
Yes sir.
Okay, okay, I'll do that. From the next session I'll make live I'll solve the questions live.
Okay.
So if there is no question, then we'll yeah, how can I okay, I in the next session I will give the YouTube link of the videos, then Puja you can get the videos there, the solved videos. Question wise there will be year wise, I mean the question and the year will be mentioned in the video's description, so you can find the question there.
Okay, sir.
Okay then, so if there is no question, then we can end the session here.
Thank you, sir.
Yeah, thank you. So you can leave if everything. Yeah, I'll solve the questions on WKB approximation as well. So I have decided each topic week wise, because I'll take only one session per week. So I have decided to solve first this potential well problem, then I'll move to perturbation theory, then time independent perturbation theory, then WKB approximation,
I,
hydrogen atom problem. So I'll try how many, if as many as is possible. So if there is no question, then you can leave the session, I think.